All right, so today we're going to be talking about feedback control. So to give a quick recap of what's gone on in the last week, we started analyzing the stability of a state space model, and we gave a lot of definitions, but we said the system was bibostable if for every bounded input, the state X was bounded. So bounded inputs lead to bounded outputs. That was, I guess, the idea behind bibostability. We then said the system was asymptotically stable if given zero input, the state X converges to zero. So if we don't touch our system at all, it just naturally converges to zero. And with these two definitions, we just came up with a general criteria for stability, which says a system is stable if the real part of the eigenvalues are less than zero, if it's continuous, or if the magnitude of the eigenvalues are less than one, if it's discrete. So continuous and discrete time systems behave quite differently, but yeah, so we talked about stability, and then we talked about controllability, which stated that if a system is controllable, we can reach any state in its state space after a finite number of time steps. So with like this definition, we were able to come up with this matrix C, which is the controllability matrix. And whenever this matrix was full rank, then we said the system was controllable. So these were quick linear algebra tests, like this matrix being full rank or the eigenvalues being some value to test whether a system was stable or controllable. So any questions about the recap we've had so far on the past week? I think these two concepts are really important going forward today. So, all right, if we don't have any questions, let's start talking about feedback control. So feedback control now, let's assume our system is unstable. And it turns out that it's in fact possible to stabilize it using feedback. So if our system is unstable, well, we got to think, why is it unstable? It's unstable because the real part of lambda I is, I guess this is a discrete time system. So we're going to say the absolute value of lambda I is greater than or equal to 1 for some I. And I guess, although it doesn't say in the slides, feedback control works for both discrete and continuous time systems. It doesn't matter. But point being, this system here is unstable because like one of its eigenvalues is unstable, or maybe many of its eigenvalues. So if we try inputting u equals kx, like literally plug in u equals kx into this system, then we'll notice that we have a new system, x of t plus 1 is equal to a plus bk times x of t. So now the system is stable if the absolute value of lambda is less than 1. Like, so if the eigenvalues of a plus bk are less than 1. So notice how we have a new criteria for stability now. The matrix A is different from the matrix A plus bk. And k is going to be something that we have control over. So hopefully we can pick some values of k where the eigenvalues of a plus bk are or have magnitude less than 1. So that's kind of the general idea here, where if we're able to find some k where the eigenvalues of a plus bk are less than 1, then the system is stable. So we're able to stabilize an originally unstable system. And sometimes this is referred to as a closed loop system. I think because like an open loop, we feed some inputs into our system. We get some output. So this is like open loop. But in closed loop, we're going to take our open loop system, take our x value, multiply it by k, and then feed it back as an input. So that's why it's called closed loop. We've just taken this, I guess, straight line here and just closed the loop. All right, and I think last thing I want to say is normally in practice, like you might see this on the homework as well for next week, where like whenever we give a feedback u equals kx, like controls engineers will always use u equals minus kx as negative feedback. So like we're going to want to make like x stable, meaning we want to make it converge to something. So we're always going to want to use negative feedback to do that instead of some sort of positive feedback, which makes it blow up. Of course, like if we switch the signs of the K matrix, it's not going to be any different, but like, I guess like in practice, like if we were to use Kx, we would just have negative values of K. So any questions about feedback control so far? All right, so let's take a look at how controllability plays a role into all of this. So if a system is controllable, then it turns out that it's possible to assign the eigenvalues of a plus bk anywhere we want in the complex plane. And this is a really good thing because if we can place them anywhere we want, then, well, we can always just place them somewhere stable. So this means if the system is controllable, we're always able to stabilize it. And if a system is uncontrollable, it may be still possible to stabilize it, but we no longer have this like freedom to pick the eigenvalues wherever we want. So we may be able to put the eigenvalues in some stable region, but it might not be our favorite choice of stable region. And the proof for this, the proof that if a system is controllable, we can put the eigenvalues wherever we want, is out of scope. But if you're interested, you can look up controllable canonical form and it'll give a pretty like nasty, but I guess good linear algebra proof that if a system is controllable, you're able to place the eigenvalues wherever you want. And as we'll see in discussion today, some choices of eigenvalues are better than others. So we're going to always want to pick our eigenvalues in the best region possible. And if it's uncontrollable, we might not always have that freedom. So any questions about how controllability plays a role into stability and state feedback control? All right. Now that we've gone over the fundamentals, let's take a look at the discussion worksheet. So worksheet today, we have a lot of, I think, intuition-based questions where we're gonna just draw things and like observe what happens and whatnot. So I'll give everyone a minute or two to just look at the first part where we're given some discrete time system and we're just going to sketch the response x of t for various eigenvalues given a zero input where u of t is equal to 0 for all t. All right, let's take a look at this together now. So given a discrete time system, it's always important to note that this system is a discrete time system. Remember that the conditions for stability are kind of different for discrete time and continuous time, and the way they behave are different. So we can write out our difference equation as x of t plus 1 is equal to lambda x of t. And since u is equal to 0 for all t, then the bu of t is going to be 0. And our initial condition is equal to 1. So from here, it really is just a matter of like plugging in values and sketching it out. And it's going to be like a geometric sequence. So like if lambda is equal to minus 1.1, x is equal to, x of 0 is equal to 1, then well, x of 1 is going to be equal to minus 1.1, x of 2 is going to be equal to like 1.1 squared, x of 3 is going to be equal to minus 1.1 cubed, so on and so forth. So we sketch it out. We're going to start at 1. We're going to go down to minus 1.1. Then we're going to go back up to 1.1 squared. Then go back down to negative 1.1 cubed, and so on and so forth. Now let's try this for lambda equal to 0.5. And it's quite a similar process, but nevertheless, we can just plug in values again. And we're going to get something that looks like this, where at time equals 0, we're at 1. At time equals 1, we're space these apart a little more, go down to 1/2. At time equals 2, we go down to 1/4, so on and so forth. All right, and then let's take a look at lambda equal to 1. So here we're going to have x of t plus 1 is equal to x of t. So it's just always going to be equal to the previous state. So we're going to start at 1, and we're just going to stay at 1 forever. So, and then if, I think this is going to be the last example I do here. Lambda is equal to negative 0.5. If we start at 1, then, well, we multiply this by negative 0.5. And we just keep doing this over and over again. And if we were to graph this, well, we would get something that looks like this, where we start at 1, we then go down to negative 0.5, and then we go back up to 0.25, and we go back down to minus 0.125. Okay, so I have a lot of drawings here. Any overall observations you can make? If you have any observations, type them out in the chat. There are a lot of observations we can make here, but negative lambdas oscillate, that's a good one. What about the size, yeah, lambda is greater than 1 kind of blow up, right? And really, we're talking about the absolute value of lambda here, where if it's negative 1.1, like we saw that it blows up as well. So, and yeah, Julie also mentions that if we have a eigenvalue like with magnitude smaller than 1, well, it's going to converge, right? Here as well, it's going to kind of converge to 0. So the observations we should make. Negative eigenvalues oscillate. And then if the absolute value of lambda is less than 1, x converges to 0. And then if the absolute value is greater than 1, then well, x diverges. And lambda equal to 1 is a very, very like special case. So we'll talk about that one a bit later. But for now, notice how it just stays as is. Okay, so let's answer part B then. So what values of lambda will result in x to converge to its equilibrium? Any ideas about this one? In other words, like, I guess for which values of lambda will x converge to 0? And hopefully you should see by now that if the absolute value of lambda is less than 1, then x converges to 0. And we define this as stable. So thought I was going to say something, but then I forgot. All right, that's fine. Yeah, let's move on. Okay, so our system is stable when the absolute value, and this is only for discrete, yeah. So this is a discrete time system. Remember that for a continuous time system, it's going to be the real part of the eigenvalues. And you can, in fact, make the exact same observations here, where perhaps it might be good to do this, in fact. Like, I'm just going to do this because I think this is really important. So our discrete time observations were that negative eigenvalues oscillate, and then if the magnitude was less than 1, it converges, right? In continuous time, what we'll notice is that imaginary eigenvalues oscillate. So it's slightly different. And then instead of the magnitude of the eigenvalue, we now care about the real part of the eigenvalue. So when the real part of the eigenvalue is less than 0, then it converges. And I don't know if Bongyi's question here is directly related to this, but I guess for a continuous time system, the criteria is different where, yeah, where the real part of the eigenvalue is less than 0, then it converges to 0. All right. So I think the key here, though, is like they're kind of different. Here it's negative eigenvalues oscillating, whereas here in continuous time, really negative eigenvalues help us. They help us converge. And imaginary eigenvalues are what make it oscillate. So, all right. Part C. All right, I'll give you some time to work on this. Overall, I didn't think it was too insightful and it was a bit confusing, but nevertheless, we shall take a look. All right, let's take a look at this now. So we have some constant input, u0. So we can write out our discrete time system as x of t plus 1 is equal to lambda x of t plus b u of 0. Just a constant input. And if our system is stable and we have some constant input, it's going to converge to a specific value. And let's suppose x of t converges to some x star, where x star is some constant value. So let's say it converged. We don't know what it is, so let's try to solve for it. And you might notice that if a system, like I guess if a discrete time system converges, then the state's going to be the same after you move one time step. So in other words, like I guess we can say that converges if x of t plus 1 is equal to x of t. So if x of t plus 1 is equal to x of t, and x is equal to like some x star, then, well, x star is going to be equal to lambda x star plus b u0. Yeah, shout out to Math 104 and limits of sequences. So we can just solve for x star by subtracting lambda x star. And we see that x star is just equal to b u of 0, 1 minus lambda. So if it's stable, then this is what it should converge to. And I think some things you can notice are, as remember that this all assumes the system is stable, meaning the absolute value of lambda is less than 1. But as lambda approaches 1, x star gets really, really large because of this denominator over here. So if we give some constant input, but our system is near stable or near unstable, like lambda is like very, very close to 1, then it's not going to decay as much every single time step. So that's why it's going to keep growing and growing and growing, because we keep feeding in this constant input at every time step. But nevertheless, if it's stable, it will converge. And as lambda approaches -1, you might notice that x star reaches some finite value, in which case it's going to be equal to b u0 over 2. I haven't thought of a exact rigorous reason why this occurs yet, but I think the intuition here should kind of be that like we're giving some constant input, but then like somehow the oscillations here are suppressing the input, making it smaller and smaller. So as that input gets smaller and smaller, then the state x is going to converge to something smaller as opposed to growing without bound. So in some sense, negative eigenvalues do help. So any questions about what happened in part C? All right, let's take a look at the next part then. I'm gonna give everyone a minute to work on this one, and hopefully this one, if you recall the definition of how to do a feedback policy from our slide on feedback control by looking at the eigenvalues of a plus bk, it should help over here. So give everyone a minute to work on this. Okay, so let's take a look at this now. So we're trying to find, or we're going to define a feedback policy law, U equals Kx, and we want to find K that stabilize the system. It's basically what it's asking. So first thing we got to do is, well, we got to plug in U equals Kx into our system. So x of t plus 1 is just going to be equal to lambda x of t plus bk x of t. And we can just factor the x of t to say that it's equal to lambda plus bk times x of t. So I think we're going to assume, for simplicity, b is greater than 0. If b were less than 0, then we just have like a very similar condition. But nevertheless, we see that the system, really the closed loop system, is stable when the absolute value of lambda plus bk is less than 1. So we can just break this up and solve for k. So we can just divide by b here. And I guess if we assume b is greater than 0, then our k values are going to lie in between this range. Whereas if b is less than 0, then we're going to be dividing by negative. So we're going to have to like flip the signs. So we're going to say that if b is greater than 0 or less than 0, then k is going to be greater than 1 minus lambda over b, and k is less than negative 1 minus lambda over b. So sometimes I think in controls, it's hard to write a closed form solution for something. But nevertheless, if we're given actual values, we could identify these policies on our own. So, all right, any questions about this specific part? We're doing much better on time this time around, so. All right, and I'm gonna skip part E, but here we're gonna do the exact same thing for a continuous time system. So as we mentioned earlier, you need to check if the real part of lambda plus bk is less than 0 here. So it should more or less be the same problem. All right. We don't have any other questions about this problem as a whole. We shall move on to the next one. And I think we should also keep in mind, I guess, general design choices for eigenvalues, where again, we kind of talked about how if we have negative eigenvalues, we're going to have some sort of oscillations. And we always want our eigenvalues in order to be stable to have magnitude less than 1. So let's keep those in mind. And I think whenever you're doing feedback control, it's really important to keep these like two ideas in mind in order to pick good eigenvalues. And hopefully by now you have kind of an idea of what good eigenvalues are, because normally you don't want your system to like oscillate out of control. And that's why you always want to pick real eigenvalues in the discrete case and purely real negative eigenvalues in the continuous case. Okay, so in the second question, we're given a discrete time system now, and I'm going to give everyone some time to work on the first two parts. It's hopefully some review, where we just ask, is the system controllable and is it stable? All right, let's take a look at this together now. So we're given a discrete time system. We have the A and B matrices. And the first question asks, is it controllable? So all we need to do is just look at the controllability matrix. And just write out B and AB and compute what that actually is. So B is going to be 1 and 0. A times B, if we multiply the two, let's see, we're going to have 0 in the first entry, and then we're going to have 2 in the second entry. So the rank of C is equal to 2, so it's full rank. So the system is controllable. And I know some people asked about this in the earlier discussion, but the order in which you like stack the vectors, whether you stack AB then B or B then AB, shouldn't matter, because switching the order of the columns of a matrix isn't going to change its rank. So I like to use B, AB, A squared B, so on and so forth, because it's easier for me to count from 0 to n minus 1 than to count down from n minus 1 to 0. Anyway, let's take a look at the second part, which asked, is the linear discrete time system stable? So again, very important to note that it's a discrete time system. And here it's just going to be an eigenvalue problem. So let's look at the eigenvalues of A, meaning we can compute the determinant of A minus lambda I, and well, it's gonna look something like this. can just multiply the diagonals, meaning it's going to be like minus lambda times minus 1 minus lambda minus 2, which can then simplify down to lambda times lambda plus 1 if we multiply both of these terms by -1 minus 2. And then you can just expand this out. And last thing we can do is just factor this out. So if we go back to algebra, remember how to factor, this is going to be lambda plus 2 and lambda minus 1. So this tells us that our eigenvalues are 1 and minus 2. So since really both of our eigenvalues have magnitude greater than or equal to 1, the system is unstable. So any questions about the second part? All right. Now let's take a look at what happens if we use state feedback. So what happens if eigenvalues equal 1? Yeah, that's a really good question. So if the eigenvalues are equal to 1, like if we gave 0 input, notice how it just stays at 1. But let's say we gave a constant input now. Let's say we gave some BU of 0. So let's suppose lambda is equal to 1 and u of t was equal to u0. In other words, x of t plus 1 is equal to x of t plus bu of 0. Then you might notice that like if x of 0, let's say, is 1, then x of 1 is going to be equal to 1 plus bu of 0. X of 2 is going to be, well, it's x of 1 plus bu of 0, which is then 1 plus 2 bu of 0. And x of 3 is going to be 1 plus 3 bu of 0. And it's going to keep like increasing over and over and over again. So notice how if you give an input, it's unstable. So this is why we say lambda equals 1 is unstable. And if we go back to our definitions from stability, remember how we also said a system was asymptotically stable if given 0 input, the state converges to 0. But you might notice that here we gave 0 input and it converged. It converged to 1, but it didn't converge to 0. So since it doesn't converge to 0, we say it's unstable. It's like the alternate way to view stability. And I think the last thing I want to say, someone asked this earlier, was what if one of the eigenvalues is stable? So what if lambda is equal to 1/2 and -2? Then is this stable? Well, unfortunately not. Again, since -2 has a magnitude 2, which is greater than 1, it's still unstable. And it's kind of like the analogy where like the rotten apple spoils the barrel, where if any one of your eigenvalues are unstable, then the entire system is going to be unstable. And it's kind of because you have like a linear combination of like exponentials, or I guess linear combination of lambda to the t's, and one of them is going to blow up. Okay, now that we've kind of talked about stability, let's take some time. Let's give you some time to work on part C and D, where we're going to derive a state space representation of the closed loop system and then try to put the eigenvalues at -1/2 and 1/2. right, let's take a look at this together now. So I think we need to start with our original system. So I'm just going to write out x of t plus 1 is equal to our state matrix 0, 1, 2, minus 1, x of t plus 0, 1, u of t. And we want to somehow give an input u equals kx and derive a new state representation. So plugging in our input, we can see that this is in fact equal to k1, k2 times x of t. So if you look at the shape of these matrices, you might notice that this is a 2 by 1 and k is a 1 by 2. So if you multiply a 2 by 1 matrix by a 1 by 2 matrix, it's going to be a 2 by 2, which should make sense. So if we do the actual matrix multiplication, we got the x term multiplying the first matrix. Thanks for the catch. Then we're going to see something of the form. We're going to have, sorry, this is a 1 and a 0. I copied this the wrong way. We're going to have k1 and k2 in the first row, and then it's going to be 0 and 0. And this tells us that our closed loop matrix, sometimes it's called ACL, like a closed loop, is just k1, 1 plus k2, 2, and minus 1. So this is our closed loop matrix where x of t plus 1 is equal to the closed loop matrix times x of t. Okay, and now let's use state feedback to actually pick our constants k1 and k2 in order to put the eigenvalues at minus 1/2 and 1/2. Like currently the eigenvalues are at 1 and minus 2, but now we want to use state feedback to move them to a new location. So the way this is going to work, I think it's a very mechanical process, but also like a very got to be very careful when you do every step. So I think there is a very precise way to think about this, meaning we want the eigenvalues to be at minus 1/2 and 1/2, right? So this means we want our characteristic polynomial to be lambda plus 1/2 times lambda minus 1/2. This is what we want our characteristic polynomial to be. And if we expand it out, we can use the difference of squares to say this is lambda squared minus 1/4. So this is what we want it to be. And we currently have the determinant of a closed loop minus lambda I. So we want this determinant to be equal to lambda squared minus 1/4. Because if the two of them have the same characteristic polynomials, well, they'll have the same eigenvalues. So we're going to want to find, so the goal here is to find k1 and k2 such that the determinant of the closed loop matrix is in fact equal to the characteristic polynomial lambda squared minus 1/4. Might seem a bit backwards right now, but once we do the actual calculations, we'll see how this works. So now let's take a look at the determinant of the closed loop matrix. if we actually do the computations, then it gets a little nasty, but it's going to be something like k1 minus lambda minus 1 minus lambda minus, we're going to have to subtract the product of these two, so minus 2 minus 2k2. And then we're just going to expand everything out. So this is going to be lambda minus k1, lambda plus 1 minus 2 minus 2k2. And expanding this term out, we're going to get something like lambda squared. If we use FOIL, we're going to get like 1 and a minus k1 times lambda minus k1 minus 2 minus 2k2. So this quantity over here is our characteristic polynomial of the determinant of a closed loop minus lambda I. And we want this characteristic polynomial to equal lambda squared minus 1/4. So from here, it's just a bunch of pattern matching where we're going to want the coefficients to match. So we're going to want 1 minus k1 to be equal to 0, since you can write this as lambda squared plus 0 times lambda minus 1/4. So we're going to want 1 minus k1 to equal to 0. And then we're going to want minus k1 minus 2 minus 2k2 to equal to minus 1/4. And if we solve this system of equations, you can see that k1 is equal to 1. And we can then plug in our value, k1 is equal to 1, into here. So then we're going to have minus 1 minus 2, which is then minus 3. Minus 2k2 is equal to minus 1/4. Algebra is kind of not the nicest. I think whenever you do feedback control, the algebra is going to, by hand, algebra is going to be really bad. So this is going to be equal to minus 3 plus 1/4, which means k2 is going to be equal to, well, minus 3 plus 1/4 is just minus 11 over 4. Dividing that by 2, we get minus 11 over 8. So this tells us that if we pick k equals 1, k1 equals 1, and k2 is equal to minus 11 over 8, we're going to be able to put the eigenvalues at minus 1/2 and 1/2. And this is going to give us some sort of like system response. So any questions about everything we've done here? In the end, it just boils down to pattern matching the coefficients. So. All right, and I think the last thing I want to say is, so we're gonna always like pick, the way state feedback is gonna work is we're gonna pick some eigenvalues first. We're gonna, like, for example here, we kind of picked minus 1/2 and 1/2, and then we're gonna find k that lets us put our eigenvalues at that desired location. And because we kind of saw earlier what kind of eigenvalues were good and bad, we saw that negative eigenvalues oscillate, and we always want our eigenvalues to be stable, meaning they have magnitude less than 1. We can always, if our system is controllable, pick our eigenvalues first and then find k by doing this calculation that makes our eigenvalues like at that desired location. So we can always pick some desired k and then, sorry, desired lambda, and then find k that matches the lambda. And if our system is uncontrollable, as I think the rest of the discussion where she talks about, you'll be able to move the eigenvalues, but you can't move them anywhere we want. So discussion is now officially over. Thank you all for coming. And if you have any questions, definitely feel free to stay around and ask.